All right, let's get started. I think we have most of the students. Today, we'll continue our discussion on pipeline microprocessor. Okay. As usual, again, a few logistical things. One more time, right? Prelim 2 is going to be scheduled on next Tuesday at 1 p.m. Please log in, right? Please, we are going to use this exam Zoom room. We'll post the link again. Please come to the Zoom room at least 5 minutes earlier, right? Just like last time, we're going to release the item pool link a few minutes before 1 p.m. And our PhDA, Lisa, right, OUA, she's going to hold a review session tonight at 8. Okay, hopefully some of you can attend. And I'm going to move my office hour today, right, to Sunday at 4:30. Mitchell, you're asking about the review, right? Prelim 2 review? Yes, I think so. I'm going to remind Lisa. All right. And a little bit more about Lab 3. We extended the deadline. Right? It's going to be due tomorrow. Please submit on CMS. I think you guys can check off by Monday, right? One thing that we notice is, we have received some of the designs, right, from you guys. There's one common issue. You look at your FSM, in case your FSM is passing the simulation, but it's not working on the board. Actually, in some cases, your FSM may not even pass some of the test vectors, right, in the simulation. So make sure that you double check your combinational, your logic for the output and next state. Make sure that one is combinational. We've been talking about this quite a few times, right? In case you already forget about how to make a combinational logic using always block, go back to lecture 9. There are a few templates, right, for both the output and next state. We are building more machine, I believe, right, in Lab 3. And also, I think currently Lab 3 report is due next Wednesday, right after the prelim. Okay, I'm gonna most likely extend the deadline for you guys, okay, most likely by 10 days, so that you guys can right after prelim, you guys can focus on Lab 4. Okay, so stay tuned. We're gonna make an announcement on the other. All right, let's come back to pipelining. I actually want to revisit this discussion, right, that we had. It's actually a very productive discussion about the intuition behind pipelining, right, about this analogy. We talk about this course pipeline, right? We talk about these 4 courses. I'm going to earn this computer engineering major. The assumption here is that you guys need to finish these 4 courses over 4 years, right? And currently, these courses are taught by these professors, right? Only using the initials here. Okay, I actually turned this into a bonus question. I got 2 very interesting answers, right? The first answer is more from the student perspective, right? So basically, if you do not do this kind of a course pipelining, we will not be able to admit the next class in the next year, right? We will not be able to admit a new class every year. So instead, we'll be admitting a new class every 4 years, right? Which is bad for the students. We actually focus on discussion from the student point of view last lecture, right? Because Cornell is a student-first school. There's also another interesting point raised by another student, right? She actually talked about the professor, right? The instructor may get burned out. I did not get a chance to touch on that point, but today let's talk about this. Okay. Think about the single cycle microprocessors case. Okay. In the single cycle microprocessor case, if you try to map that one right into this scenario, what does that mean? It really means that instead of taking a new class, right, every single year, we again take a new class, admit a new class every 4 years. Right? So this is basically our single cycle microprocessor. So for each course, we still have a different professor, right, teach that course. Agree? Right. So this is basically a single cycle processing cycle, and over here the cycle time or the clock period is not 1 year, right? It's 4 years. So in this case, of course, the next batch of student, they are losing, right? Who's the winner here in this case? Who is benefiting, right? Who gets the benefits in this case? In a single cycle microprocessor. Right, the student, the current batch, right? Yes, Mitchell, you're right. The current batch, they still need to take these 4 courses, right? Each year, and then it takes 4 years to graduate. We talk about this concept called latency. Right? Really, the throughput of this course pipeline is slower now, right? It's lower now. It's not every 4 years. But again, let's focus on the instructors, right? Really, in this case, yes, Stephen, you're right. In this case, the professors, right, only have to teach 1 class, 1 course every 4 years. Okay, so that's our course, right? The professors are not burned out anymore. This is the really the difference, right, between the single cycle and pipeline processor. If you look at this, if you think about things from this perspective, right, basically the professors are sort of underutilized. Agree? Right? And the whole point of doing pipelining, the whole point of doing this kind of right, so we divide it into stages, right, and we try to push in, right, a new class of student every single year. The whole point is first, we increase the throughput of the system, and also, all the human resources, right, in this case, are 100% utilized. That's one of the gist behind pipelining. Same thing for the microprocessor. Right? What we are doing here is that, instead of having some of the stages idle, right, for period of time, we are dividing this into 5 stages. Right? This is our 2300 microprocessor. What is the name of the first stage? I just want to make sure that you guys still remember the names, the acronym. First stage, what's the acronym? Fetch, okay, IF, right, IF. Second one, decode, right, ID. Third one, EX, right. Next, what's the acronym? Next one, this one, the memory one, MAN, right, very good, Emily. And write back, right, WB. Okay, so what we are doing is, we are making sure that all these hardware resources are fully utilized. Okay, so this is basically just behind pipelining. That's how we get the speed up, because all the resources are busy all the time. Of course, there are some trade-off, right? It's not like we can just evenly divide up the critical paths. In reality, in practice, it's not like if you run a single cycle microprocessor, we get, let's say, 1 gigahertz. Okay, 1 gigahertz. Let's say that's the frequency. It's not like if we just divide it into 5 stages like this, we will automatically get a 5x improvement in frequency. Like we'll get a 5 gigahertz processor. That's usually not the case, because we do need to add additional. You'll see we will need to add additional, right, logic. Some of them are already showing up here, right? So we actually need to add additional, at least, wires, right? So those also contribute to delays. And today we're going to see we need to add additional muxes as well. All right, so there's always a trade-off, but in general, right, if the pipeline is busy most of the time, we get performance improvement. All right, any more questions about intuition behind pipelining? Okay. Right. If not, let's talk about some of these non-ideal cases, right? One more time, right? Ideally, so the pipeline is always busy, right? All the resources are busy, but there are cases where we have to slow down the pipeline, right? Where we have to stall the pipeline. This is where we have data hazards. We talk about we mainly focus on these ALU instructions or R-type instructions last time. Today, we're going to look at some of the other instruction type as well, like load and branches. You'll see the implications of those instructions in terms of data hazards. And if you look at this example, right, this is the one that I showed you. If you do not do anything, we will have an incorrect execution, right, in this case, because the first instruction add, right, is not going to write this R1, updated R1 value back until cycle 5. But if you look at the second instruction in the pipeline OR, it's going to read from the register file, right, in cycle 3, which is bad. Okay, again, we are not really building a time travel machine, right? So this is bad. We somehow, right, need to resolve this. Okay, same thing here and same thing here, right? Because we are writing to a register over here. This is a trickier case, right? Although this seems to be happening in the same clock cycle, but really we are writing to a register. The new value will not show up until the next clock edge. Right? So this is this where we also cannot, just this is also where we are reading the old value. We also need to do something over here to fix the data hazard. All right. So we talk about two solutions. Actually, both solutions are pretty simple. I call them the dumb solution. If you see, we are going to talk about smart solution, a much smarter solution today. This is where a compiler can step in. Compiler, in this case, will insert these dummy instructions called not or no ops. Right? We agree that we actually need to insert a list. If there's a dependency, right, between two consecutive instructions, we need to insert at least 3 no ops, right, between these instructions, so that the dependency, right, is resolved, the data hazard is fixed. Right? And this is the quiz question, right? I should ask you guys to insert the no ops for me to fix this instruction sequence. What was your answer? Actually, most of the class got it right. Look at your answer. Do you guys still remember how many no ops do you have to insert? Very good. 2, right? 2 no ops. So first, where's the data hazard, right? If you look at the first instruction, we are writing to R4, right? Over here, R4. And we have a read, right, from R4 in the third instruction add I. And we have another read in this OR instruction. In both cases, we are facing a data hazard, right? Because this instruction, the distance, right, between sub and add I, and also distance between sub and OR is not long enough, right? We actually need to make sure they are at least 3 instructions apart. That's where, but we do already have one, right? We have one here. So that's where all we need to do is to just add 2 more. Okay, that's how we can resolve the hazard. The correct answer is 2. Right? I'm glad that most of you got it right. Any questions about this? This is where the compiler is doing some additional work, right? Some extra work to insert these instructions in the program binary or the assembly code. And hardware does not need to do anything. In another scenario, so this is where we don't have to count on compiler, right? We can also try to make the hardware more aware of this data hazard. In the next lecture, next Thursday, we're going to be talking about how we can detect this kind of hazard on the fly in the pipeline. So let's say we already have that kind of a detection mechanism, right, in our hardware. So that's where the hardware can basically insert this bubbles. So these are basically very much similar or the same with no ops. But again, this is inserted on the fly at runtime by the hardware, okay, not by the compiler. Compiler is doing the compilation offline. Okay, that's also one way for us to, also one dumb way for us to resolve this kind of data hazards. Good. So last time we talked about this concept called CPI, right? CPI. Do you guys still remember what is the full name of CPI? This is an important performance metric to measure the efficiency of microprocessor. Okay, very good. Kevin, Katie, Emily, you all got it right. Cycles per instruction. Okay, so what is the ideal CPI in our case for pipeline? 1, very good. Okay, But what if we have this data hazard, right? What if we have to insert these no-ops or bubbles? Is the CPI gonna increase or decrease? Increase, right? Very good, right? We will have more cycles. We have to spend more cycles per instruction, which is bad. Okay. So basically, inserting this, right, inserting these bubbles will increase the CPI, the cycles per instruction. This is something that we want to avoid if possible. Okay. Let's see how we can do this in some cases. It's not like we can avoid all possible data hazards. In some cases, we do have to insert the bubbles. Okay. But there are actually some cases where we can have a much smarter solution. So this is where we introduce the so-called bypassing or hover forwarding. Forwarding. So it's actually we are literally forwarding the result from a previous instruction. That's why we call it hover forwarding. So let's look at this sequence again. Okay. Let's focus on the first instruction. Can you guys tell me where exactly is, where do we know the result of R1? Forget about when we write it back. When do we know the result? Which cycle? Is it cycle 6 or cycle 4? Right. Many of you got it right. You can either say that we got the result at the end of cycle 3, or we get the result right at the start of the cycle 4. Okay. Since this is ALU instruction, right? We do the add over here. We already have the result somewhere at this point. Make sense? Okay. Then really the solution is why don't we wait until cycle 5, right? Why don't we wait until we write the result back to CC the register file as CC5? Why don't we just somehow forward the value, the new value of R1 right away to the next instruction? So how do we do that? Okay, let me show you a couple scenarios first, and I'm gonna ask you about the third scenario. First, if I want to forward from this is add, right? Add to OR. I'll just have this ALU over here in cycle 4. I'll have the ALU read from this pipeline register instead. Okay, make sense? I'll read it from somewhere here. Okay, I'll forward the value from this pipeline register to this ALU directly. What is the name of this pipeline register? It's called EX/MEM, right? So what we are doing is we basically forward. Later on, we actually will define this path. Right? This path, you can just call it path of MEM to EX. So we are really, so when this addition, right? The add instruction is in the memory stage. Let's focus on cycle 4. Okay, let's just focus on cycle 4, CC4. This is where add is in the mem stage, right? Okay, basically that's where we forward the result of the value of R1 directly to the ALU. This is also where OR, right, is in the EX stage. That's how we do the forwarding. Okay, hopefully this makes some intuitive sense, right? I'm gonna show you how this is built in hardware. Okay, so there's a question. So ALU will read from the register it writes to. Yes, that's the gist, right? So you can imagine that in the hardware, in the actual hardware, there's this backward pass, right? Although in this logical, right? This is really a logical view. This is really a temporal view, right? Instead of physical view. In the temporal view, it's like we are forwarding, right? But really, the ALU will read from directly read from this EX/MEM register in CC4. Okay, and there will be some muxes, of course, right? In front of the ALU, some extra muxes. Make sense? How much, there's a question, Amber's asking, how much does the overhead needed for detection and forwarding? Right, this is an excellent question, right? Like I mentioned, this is a trade-off. There will be actual muxing, right? There will be actual wires, right? There will be also actual detection logic, right? When do we forward, when do we not forward? So we just have to look at the critical path in the end, right? And see how much is the increase that we are causing to the critical path. Okay. Actually, in many cases, this will not increase the critical path that much, fortunately. Okay. But there will be some increase, and at least the decrease of CPI will outweigh the overhead of the frequency in most cases. We'll have a more detailed discussion later on to see different kind of trade-offs in the pipeline. All right, so this is the first case. Does it make sense? Right, we are basically making this data forwarding from MEM to EX. How about the second case? How about this one? How do we forward? Any proposal? What do you do? At which cycle do we forward? Can we still forward from CC4? Or we need to do it in a different cycle? Right, very good, Jonas. Not CC4, right? We want to do it in CC5. Okay, we want to do this, right? Because the value of R1, the new R1 for add, right, for the first instruction has already traveled to this next pipeline register, right? This is a MEM/WB, right? So in CC5, at CC5, MEM/WB, this pipeline register holds the latest value, the new value of R1. And we can forward from here and directly to the ALU, okay, for the sub instruction. Is it clear? But let me ask you guys a question. So if this is still not too clear, right? So again, this is where we can do the so-called WB to EX forwarding, right? Before from the WB stage and to EX. Okay, right. So Alma is already asking the obvious question, right? This is also the question that I'm going to ask the class. Why can't we forward? Why can't we do this kind of forwarding? Why can we still forward from MEM to EX? Why don't we do it in CC4? Oh, that instruction entered the ALU already, right? Very good. I think most of you are saying the same thing. Okay, first, this forwarding, if you look at this this arrow that I drew, right? We are forwarding from CC4 to CC5. First, it means that we are forwarding from this register, right? It means that we are forwarding from this register, EX/MEM, right? This register. Let me highlight this one. To the ALU for sub. But when do we do the subtraction? In CC5, right? We're doing the subtraction. We're doing this ALU. We're using ALU for the subtraction, for the sub instruction in CC5. But in CC5, this register, the EX, right? This register, let me highlight this again. This register no longer holds the value, right? No longer holds the value of R1. Does it make sense? At CC5, if you look at this register, it no longer holds R1. What value does it hold? In CC5, it holds the result of the OR instruction, right? R4. Okay, so that's why we cannot do this kind of forwarding. Make sense? Is it clear? No, Alma? Right. Instead, we want to do this. Okay. So really, we actually want to do the forwarding, right? Within the same clock cycle. which is right in this logical view, which makes sense, right? All right, so now let me ask you guys a bonus question. Okay, here's a bonus question. So one more time, don't if you have an answer, right, don't put it in the chat window. Raise your hand. How do you do this forwarding? What do we do? Where do we forward? Is the question clear? Right. So tell me from which stage, right? The source stage of the forwarding and the destination stage of the forwarding. We have talked about mem to ex, right? Not mems. Right. Mem to ex and WB to ex. How do we forward from at to end? I'll do the countdown. If you guys have an answer, right, raise your hand. Okay. 3, 2, 1, go for it. Lauren.
Because R1 was the second input in the subtraction instruction, you can forward from like that input to the ALU to the
At which cycle do we do the forwarding?
CC5.
CC5, okay. Very good. CC5 to where? To
CC6.
To CC6, can we do that? It's actually not a good idea, right? To do forwarding across cycles. We just talk about that, right? So really, you want to forward at this point, right? CC6, because you want end, right, to get the right value over here. Is that right?
Oh, okay.
But
yeah.
at CC5, let me just talk about this, right? At CC6, right? This register, this mem / WB register no longer holds R1, right? But this is a very good attempt. All right. Let me also ask the second student, Jacob.
Can you still do what she said, but instead of doing it through CC6, you just put it into the part right before in CC5 from the output of the register file?
Like here. So again, you want to do the supporting at this stage, right? CC5, sorry.
Yeah.
Okay.
So like the bottom input of the ALU in the third instruction, you could just put in one of the outputs of the register from the next instruction.
Here? Like here?
Yeah.
Okay. Excellent. Okay. All right. Let me ask. I think some other student also raise hand. Mahmoud.
Wait, so I think now I'm a bit confused because I thought forwarding wouldn't be necessary at this stage because by then R1 would already be defined within the register. Okay, all right, good question. Okay, so let's talk about this. Right, I think we already have the correct answer. So let's first resolve the question by Mahmoud, right? So what he's really asking is, what's wrong with this, right? Sorry. We talked about this last time, right? We are writing to a register, right? When we write a register, the new value, a register is like a delay element, right? The new value will not show up until CC6. But at CC5, right, we are already reading from the register file. So that's where we are reading the old R1. Is it clear now? Oh yeah, so that's why. This is not good, right? And also, ideally, right? So we really want to forward somewhere from here to here, right? At CC6 to resolve the data hazard for end. But the problem is that this addition, right? This guy has already retired from the pipeline. There's no way that we can forward. So really, the answer is this. Okay, which is actually pretty cool, and it's a very subtle solution. Okay? This is pretty subtle. What we want to do is, over here at this cycle, right, CC5, we have the correct value of our R1, right, in this pipeline register, mem / WB.
at this point, we actually want to forward to this signal. Basically, we overwrite whatever is being read from the register file, and we put the mux here, and then we put it into this pipeline register. So that in the next clock cycle at CC6, the ALU will be operating on the correct input. Is this clear? If it's not clear, then make sure you guys ask. This is pretty important, okay, for you guys to understand the, the essence of forwarding. Alma, you have a question?
Yeah, I didn't really catch what you meant by saying overwrite. Like, what is the mux overwriting?
Right, so we are going to be talking about this, right? I'm going to show you the hardware, right? So basically over here, we are supposed to read out data A, right, from RF. Is it clear?
Yeah.
This line, right? So this is data A from RF. But the one that we read out from RF is old, right? It's the old R1. So instead of using this one, instead of using this old data A, so why don't we just use this value? Then we push this one into the pipeline register. That's where we need the mux, right? If we indeed do the forwarding, we need to choose this blue arrow instead of the data A from RF.
Oh, okay, I see that. Thanks.
Okay. All right, this is forwarding, right? How forwarding works. This is pretty cool, right? We look at what we just got. Actually, this is the pipeline result, right? This is a pipeline result. This is the abstract diagram of the pipeline, right? Let's see how we can do the forwarding. So this is the one result forwarding, the pipeline processor. Hopefully, you guys are already sort of comfortable with this diagram, right? They are quite a bit of wiring, right? One more time, the blue wires are the control signals, and the black lines are the data signals. This is result, right? Result forwarding. This means result. Okay. Result. I'm going to quickly show you the diagram with forwarding. You see that now that we have some additional muxes in front of the ID/EX pipeline register. Okay, so this is the mux that we just talked about. Okay. This is where we make a choice between, do we take the value from the forwarding pass, or we take the value from the RF. Okay, so, and this is the forwarding pass. See here. All right. Okay, this is one that I'm highlighting. We also need some additional muxes, of course, for data B, right? Because in some cases, data B may cause a data hazard, right? And we have some additional muxes now for in front of the ALUs. That's where we choose, whether we take the one from the previous stage or we take the forwarding pass. Again, there's some forwarding pass, okay, from MEM stage, and some forwarding pass from the WB stage. All right, hopefully this makes some intuitive sense, right? We're gonna look at some concrete examples pretty soon. Maybe actually let's just look at one right away. This is the one that we just discussed. Over here, I'm assuming that the add, right, this addition is already in the pipeline. Right now it's in the EX stage, right? And OR is in the ID stage. Okay, so when does data hazard occur? It's going to be the next cycle, right? So when we execute OR in the ALU stage, that's where we need to trigger the data forwarding. So in the next cycle, when add is in this stage, the MEM stage, or is in the EX stage, we are going to be activating this yellow pass. Okay, so this is where we have the updated, sorry. This is where we have the updated R1. Okay. R1 is gonna travel through this, the updated one is gonna travel through this yellow pass and hit this mux. Okay. Again, this data forwarding pass becomes the backward pass, right? In the physical hardware. This is the yellow one, is the the forwarding pass. Okay. All right. Is it clear? Let me ask you guys just to make sure in the next clock cycle, right? Subtraction is going to enter EX. We also need to resolve the hazard for R1, right? So in the next clock cycle, are we going to be using the same yellow forwarding pass or a different one? Yes or no? Are we going to be using the same one? Okay, very good. We're going to be using a different one, right? Because we want to forward R1 produced by add. But add has moved on, right? Add has moved on to the next stage. So that's why we don't want to use this yellow pass anymore. Instead, we want to be using this pass for sub over here. Okay, now that add is in the double, this is write by stage, we want to use this pass, right? Okay, and we hit this mux. Now this mux has 3 inputs. We have the forwarding pass, we have the the original one, right? There are actually 2 kind of forwarding pass, right? One from mem, one from WB, and the original pass. That's why we have 3 inputs in this case. Okay. There's a question, Alma?
Yeah, in this slide, is there 2 like forwarding going on from add to sub and?
Yeah, that's right. You're reading my mind. I'm gonna talk about this, right? The next one right away. Okay, but it's first one is clear, right, guys? This one, so this is where we are doing the forwarding for sub. Okay, and then let's talk about this guy, right? This line, this pass. Okay, so this is related to the bonus question, right? This is where we want to forward from R1, this R1 addition to this R1. This is where the yellow, the second yellow, the second part of this yellow line, right, is really doing. What we want to do is, we don't really want to take the old value from the RF, right, for this end instruction. Instead, we want to take the forwarded value over here. And that's why we have a separate mux over here. We have 2 input mux here. Okay. All right. There are a couple questions. Let me answer each one of them. What do the mux controller connect to? Excellent question, Amanda. Right, again, over here, we are making some, simplification. We're not really showing the controller. We're going to be talking about that next time. So we are going to be talking about how can we detect this kind of forwarding, right? And what kind of control logic do we have to do? But for now, again, just assume that things will just, right, this control signal will just show up at the right moment. Okay. And also, on my thing, I saw we cannot forward twice in the same cycle. We can forward twice, right, in the same cycle, but we cannot forward across different cycles, right? So really, if you come back to this diagram, right, we are actually doing 2. We are activating, right? We are really enabling 2 forwarding passes in the same cycle in CC5. In this abstract logical view, right? We have 2 blue lines here in cycle 5, and these are reflected. Let me come back to this one. These are reflected by this yellow line, right? We are basically doing forwarding here, and we are doing forwarding here. All right. Any more questions? Okay, good. Let's move on. So this is basically, what we have, right? With the hard forwarding. Actually, I was planning to talk about trade-off between performance and cost, right? But some of the questions already, I think some of you already raised this question, right, early on. really, if you look at the new hardware, right, indeed, we are increasing the delay. Right? In the EX stage, we are also increasing the delay in the IT stage. Right? So in the end, that's where we basically have to look at this whole thing holistically. We calculate the critical path for the entire pipeline. Right? So when we do the time analysis, we need to do the time analysis between each pair of the registers, and then we see what is the final critical path. Right? That's how we determine the clock frequency. The good news is in most cases, these are fine. Right? Of course, we will be paying some overhead, but really the benefit outweighs the overhead in this case, because we don't need to insert bubbles anymore. Right? That is for this sequence of instruction.